everybody, welcome to the Institute. We're going to go over this problem. This is actually very similar to our acceleration on an incline lab, and actually also our friction on an incline lab. So it's a great one to kind of totally understand. So, I mean, if I was going to do anything, I would put a little heart by it because it's a good problem. So we have this block that's 125 kilograms. They tell us what static friction is, this 0.545, and they tell us what kinetic friction is, this 0.202. So the first question, part A, you really don't have to do anything with kinetic friction. It says at what angle would the block just begin to slide down the incline? So this is that situation where we increase this angle up until this block started to slide. And so if you remember, we went through that process that you can actually find the angle which that happens. What I'm going to kind of do is actually look at this from a free body diagram standpoint. So we've been doing this. We've been breaking the weight of an object up into its perpendicular force and its parallel force, which are actually the components of the weight. And then we also have the normal force acting on it, which would be opposite the perpendicular force and would be equal to the perpendicular force. So the normal force and the perpendicular force are equal to each other. I'm just going to write this. Fn equals F perpendicular. So that's kind of important. And then on an incline, assuming it has friction, then friction is going to try to keep it from sliding down the incline. Now, in the first case, we're looking at a situation where it just begins to slide. So what we want is basically F parallel is just barely larger than the friction force. But so I'm going to draw it the same size to start off with. And this one, since it's just beginning to slide, would be our static friction force. So what we did before with this particular problem is we said, okay, if I want to figure out what's going on, I'll just kind of go through this process. We know that F parallel would be the same as your static friction force. So therefore that would equal mg sine theta. And F perpendicular would equal your normal force, which means it would equal mg cosine theta. And then the neat thing is, if you take F parallel and divide by F perpendicular, it would be the same as friction over normal force, or as these, would actually equal the coefficient of static friction. And then when we did that, we kind of noticed, hey, the m's cancel out, the g's cancel out, and sine over cosine is the same thing as the tangent of our angle. So that's where that came from. Now, when we did the lab, we actually were trying to calculate the coefficient of friction, so we were taking the angle and taking the tangent of it to determine what that coefficient is. This time, you're actually trying to find the angle. So the opposite, or if I want to bring this tangent over the other side, I have to use the inverse tangent. Very good. So that's how we're going to find that angle. So that's part A. But I want to go kind of through the process since we're doing the problem. Figured I'd do all the little pieces. The second one, if the incline were at 75 degrees, what would be the acceleration of the block? So for part B here, we're trying to find the acceleration of the block. So acceleration, according to Newton's second law, should equal the net force divided by the mass. But in this particular case, if it's going to actually accelerate down the incline, what we're going to find is this friction force is no longer going to be static, and it would be something smaller than the parallel force. So I'm going to draw it a little bit smaller here, just so we can kind of see that. So we'd have a smaller little friction, but now this is going to be kinetic friction. So the net force would actually be technically the sum of these two forces, but since they're in opposite directions, we say the difference between them. So we'd have F parallel acting down the incline, and we'd have kinetic friction acting up the incline. And then we would divide that by the mass of the object. And then all we have to do is put in, how do we calculate those? Well, we've already shown how to calculate the parallel force. it just equals mass times gravity times the sine of theta. And then friction force, just kind of a reminder, the kinetic friction force is equal to the coefficient of friction times the normal force, like that. But we kind of pointed out earlier, the normal force is equal to the perpendicular force. It's actually true regardless of what exactly is going on. So friction force can also be found, or kinetic friction in this case, can be found by taking the coefficient of kinetic friction times the perpendicular force. And we know how to find the perpendicular force. It would be mg cosine theta. So we're going to plug that in. So that's what I'm going to have here. I'm going to have minus mu k, coefficient of kinetic friction, times m times g times the cosine of theta. And all of that is divided by m. Now, if I take mg sine theta divided by m, the m's will cancel. If I take mu k mg cosine theta divided by m, the m's will cancel. So since there's an m here and an m here, I could factor those out and cancel out this m. So bye by m, bye by m, bye by m. And when I do that, I simplify my acceleration into g times sine theta minus my coefficient of kinetic friction times g times cosine of theta. And bam, we got a nice little equation for finding this. And we did this in our lab. You were actually measuring the acceleration and the angle and then using it to find mu k. So kind of similar that you were doing it kind of a slightly different situation, but it works out the same. Hope you enjoyed.